Welcome to this Deep Dive Explainer. Today, we're taking an unhurried, rigorous journey into the fundamental atom of literally all computation, the bit. Whether we're talking about a neural network weight, a token probability in a large language model, or the incredibly complex description of a quantum circuit, absolutely everything traces back to this single binary distinction. So let's dive right into this and build our understanding from the ground up.
Here's our roadmap for today. We'll start by defining exactly what a bit is, explore the mathematics of manipulation, and then learn how to measure surprise with entropy. After that, we'll look at the hard limits of computability, tie it all into real-world AI applications, and finally, cross the quantum bridge.
Section 1. What is a bit? Foundations of info. Now, you might be thinking, a bit? Really? Isn't that entirely too elementary? But trust me, it's not. It is the absolute core of every advanced AI and quantum concept you'll ever encounter. The formal definition was established by Claude Shannon back in 1948, which effectively founded information theory. And Shannon had this genius insight. Information isn't defined by its meaning. Instead, information is defined by surprise. It's all about the resolution of uncertainty. You see, a bit doesn't carry information just because it's a 0 or a 1. It carries information because it could have been either. It represents exactly how much you didn't know before an event actually occurred.
Let's break down the simple math behind this using a fair coin flip. If we want to calculate the information content of that event, we take the negative log base 2 of the probability. So, for a perfectly fair coin, the probability is 0.5, and the negative log base 2 of 0.5 perfectly equals exactly 1 bit of information. On the flip side, no pun intended, if an event is absolutely certain to happen, the probability is 1, and the math tells us the information gained is 0 bits. There's no surprise, so there's no information.
And you know, this brilliantly illustrates one of the absolute most powerful ideas in all of computing. A bit is just an abstraction. Whether we're using a transistor shifting between low and high voltages in a massive GPU, a magnetic domain on a hard drive, an optical disk pit, or, get this, even a superconducting circuit shifting between ground and excited energy states in a quantum processor, the logical behavior remains completely identical. The logic is entirely independent of the physics. And it's exactly this profound separation of logical abstraction from the physical substrate that allows computation to scale across totally different technologies.
Section 2. The mathematics of manipulation. Boolean algebra.
Okay, so we've established the abstraction, but how do we actually manipulate it in practice? We do it using Boolean algebra, which was actually developed by George Boole nearly a century before the first electronic computer even existed. Every single classical computation boils down to and, or, and not operations. But the absolutely crucial point I want to highlight here is De Morgan's laws. These laws state that you can invert combinations of and or gates using not gates. Why does this matter? Well, because when you're an engineer optimizing neural network inference logic, or you're out there designing quantum oracle circuits, De Morgan's laws let you elegantly swap and or operations at the simple cost of a not gate. It's a real game changer that enables highly efficient hardware implementations and model compressions.
Let's step on to the pivotal linear algebra bridge. We can represent a single bit as a column vector in a two-dimensional space. In a classical system, if you have an n-bit state vector, exactly one entry is active, represented by a 1, and all the rest are zeros. But here's where we need to pause and look at the quantum side. In a quantum n-qubit system, you just completely remove this classical restriction. All entries can have non-zero amplitudes simultaneously. This exact mathematical structure is the fundamental root of quantum parallelism. It's that precise moment where the classical rules give way to quantum potential.
Section 3. Measuring surprise with entropy. Shannon entropy.
So what happens when our bit source isn't perfectly fair and equal? If a source produces bits with a bias, the average information content actually changes. Shannon answered this with the concept of entropy. Say a coin lands on heads 90% of the time. Well, the outcome is highly predictable, right? Because the surprise is so low, the actual information content just collapses. According to Shannon's formula, the entropy drops from a perfect 1.0 down to just 469 bits. A highly predictable outcome drastically, literally, reduces the actual information you gain.
And connecting this back to our broader journey today, Shannon entropy is the classical baseline for something much, much larger, von Neumann entropy. Von Neumann entropy measures the information content of quantum states. Every single time researchers work with quantum error correction or calculate quantum channel capacity or attempt to prove quantum advantage, they're relying heavily on von Neumann entropy.
Understanding the classical Shannon baseline is an absolute non-negotiable prerequisite for grasping these advanced quantum metrics.
Section 4. Hard limits of computability. What bits cannot do.
Let's zoom out for a second to the cosmic mathematical walls that govern all computing. Bits can encode any finite information, sure, but there are hard mathematical limits on what machines can actually compute. Let's let the math breathe a bit as we trace this history. Back in 1931, Gödel proved that true statements exist that simply cannot be proven within any consistent formal system, which severely limits what we can guarantee in AI verification. Then in 1936, Turing introduced the halting problem, proving no program can always decide if another program will eventually halt. By 1953, Rice's theorem showed that all non-trivial semantic properties of programs are undecidable, meaning formal safety guarantees for AI agents are fundamentally limited. And jumping to 1997, the no free lunch theorem mathematically proved that no machine learning algorithm outperforms all others across every single problem.
So the crucial point of contrast here, and honestly this is something that is widely misunderstood, is that a quantum computer is not inherently more powerful in terms of what problems are technically solvable. Qubits cannot solve the halting problem, they cannot break all encryption simply by magic. What they can do is solve certain specific, already computable problems much, much faster. Quantum advantage is entirely about computational complexity, the speed and efficiency of solving a problem, not computability, which is whether the problem can be solved at all.
Section 5. Real-world AI applications. Real-world context.
All right, let's bring this lofty theoretical physics and math crashing right back down to the daily pragmatic reality of an AI engineer. Because bit-level thinking is what actually drives the most critical decisions in modern AI products. When engineers quantize a model, they're reducing weights from 32 bits down to 8 or even 4 bits, very carefully trading accuracy for a massive reduction in memory. Tokenization relies entirely on vocabulary size dictating the bit width of integer IDs. And consider the key value, or KV cache, in large language models. If you want a 100,000 token context window and you're using float 16 precision, that demands roughly 50 gigabytes of memory just for the KV cache alone. The raw, unavoidable reality of bits dictates the physical infrastructure required to run AI.
To summarize the harsh engineering trade-offs we see in the field, there are a few very common traps even the experts fall into. Assuming a 32-bit float is always the safe default completely ignores the very real engineering trade-off between precision and memory costs in a production environment. Ignoring data entropy is another big one. If you have heavily biased label distributions in your training data, you drastically reduce the effective information per sample, which really harms generalization. And of course, as we just discussed, conflating quantum complexity with computability leads to completely unrealistic expectations of what future hardware will actually be able to do.
Section 6. The Quantum Computing Bridge, Beyond Classical Bits.
We're going to wrap up today by looking exactly at the absolute edge of classical computing limitations. I want to leave you with this lingering, provocative thought, straight from the heart of quantum computing research. We know a classical n-bit system can only occupy one of 2 to the power of n states at any given moment. But a quantum system can have non-zero amplitudes across all 2 to the power of n states simultaneously. So, what does it actually mean to read the result? And why can't we just read all of those amplitudes directly? Understanding the transition from classical bits to quantum states means wrestling with this exact mind-bending limitation of measurement. It is the unresolved quantum horizon, and frankly, it's where the future of information truly begins. Thank you so much for joining me on this explainer, and keep questioning the foundations of the technology around you.